A gente vai ter um seminário interessante hoje, porque ele é um pouco diferente dos que nós estamos acostumados, porque o nosso colega, ele é estrangeiro, Mr. Erol Akpinar, is that? Okay. So it will be in English. It will be about determination of the structure of some liotropic, chiral, nematic, and racemic nematic phases by small angle X-ray scattering. So please.
Thank you. Okay, first of all, I would like to thank you to come here to listen to me. I will talk about some experimental results related to my PhD thesis, but not complete because it takes 2 hours maybe. Today I will only some parts of PhD thesis is represented. First, I will give some basic information about liquid crystals. Then I will talk experimental results. As you know, liquid crystals are intermediate phase between solid and liquid phases. And so the liquid crystal phase has some properties of both phases. For example, liquid crystals are fluid-like liquid, and they are anisotropic like solid. In the solid structure, molecules have certain position and certain orientation. So we can say that solid phase has long range positional and orientation order. In the liquid phases, liquid molecules are in random positions and motions, and so there is no positional and no orientational order. When we obtain liquid crystal sample, molecules lost some positional order, but there is still long range orientation order. And this can be represented by okay, and this is called as phase director. And liquid crystals are divided by two main classes. One is thermotropic, the second one is liotropic. Thermotropic liquid crystals are produced by heating suitable solid. And this means that the phase sequences can be obtained by increasing the temperature. In liotropic systems, the phases can be obtained by the solution of an amphibolic molecule in a suitable solvent. Generally, the water is used as a solvent. So here, the micelle formation is very important in liotropic systems because the building blocks of the liotropic systems are micelles. And here, this is the example of an amphibolic molecule, potassium fluorate or dodecanate, and it has two different parts. One is hydrophilic, the second part, this part is hydrophilic, which means that it can be dissolved in water, and this part is hydrophobic tail. And it can be understood from the name hydrophobic. This part is not soluble in water. But when these amphibolic molecules added to this large amount of water, and there is an equilibrium between the surface of the solvent, water, and the monomer in the bulk. As the concentration of the amphibolic molecule is increased in water, an equilibrium is reached where the structure, so-called micelles, are formed. In this structure, hydrophilic parts are existed on the surface of the micelles, and they protect the hydrophobic tail from the surrounding water. And near this concentration, or above this concentration, micelles starts to form, and this concentration is called as critical micelle concentration. And near and at this concentration, micelles are spherical in shape. And if you increase the amplified concentration in the water, and water crystallization phases are observed, depending on the micelle shape. If the spherical micelles are arranged in the cubic structure, the phase is called as cubic phase. And if the micelle has cylindrical shape and nematic NC phase or nematic calamatic phase observed, and if you increase the amplified concentration, hexagonal phase is formed. And the other shape of micelle is disc-like micelles, and now nematic phase is also observed like NC phase, and if you increase the amplified concentration, laminar phase are formed. Okay, as I said, there are 5 common liquid crystal phases: laminar phase, hexagonal phase, cubic phase, nematic and kinematic phases. Only last 2 phases are subject to this thesis. But I will give some information about the other phases. And in laminar phase, both amplified molecules forms the bilayer, infinitively large bilayer, and water molecules are sandwiched between 2 layers. And as you see from this figure, there is one-dimensional repeating order, perpendicular to the large surface of the bilayers. In hexagonal phase, infinitively long cylinders are arranged in hexagonal array. So there exists 2-dimensional repeating order in this phase. And in the cubic phase, the micelles has certain position in 3 dimensions, x, y, z, and so we can say that there exists a 3-dimensional order. Okay, nematic phases and kinematic phases are subject to thesis, so I will talk about these phases largely. And nematic phases can be obtained by mixtures of amphiphilic molecules and water. They can be obtained by this type of chiral amphiphilic molecules or racemic amphiphilic molecules. For example, here there is an example, the alanine hydrochloric odor is ester, and this is the ammonium chloride. And in nematic phases, micelle shapes different phases. For example, ND phase. In ND phase, micelle phase consists of disc-like micelle, and in NC phase there is cylindrical-like micelles, and it can be biaxial shape. But exactly, I don't know ND phase. I am here to learn this type of ND phases. And in these phases, as you can see from this picture, micelles oriented in this direction. This is called phase direction. And in the NC phase, the phase director in this way. Another important liotropic phases, kinematic phases. These phases can be formed by 3 ways. You can add a suitable chiral solute to a micellar nematic phase, and you can use suitable poorly amphiphilic enantiomers and using chiral solvent. These two ways is very common, but not common way to obtain kinematic phases. In this phase is also called induced kinematic phases, and this the phases obtained by this way is called intrinsic chiral nematic phases. In chiral nematic phases, mite cells turn around to helix axis to complete the 2-pi rotation. This is a very important parameter in the chiral nematic phases. And the distance between two original mite cells after the complete of 2-pi rotation is called pitch or helical pitch. Okay, this is the characteristic oriented fingerprint texture. Sometimes this is called spaghetti-like texture. And these 3 lines corresponds to the helical pitch. I believe I give here half pitch to explain how it can be observed under polarized microscope. And this is the glass surface, microslide glass surface, and this is the dark places where the optic axis of the phase is parallel to the polarized light. And another important parameter in the kinematic phase is helical twisting power. And it is given by this equation. X is the enantiomeric purity, mole fraction of the enantiomer in the mixture. R is the enantiomeric purity, and it can be the HTP is obtained from the pitch measurements by plotting P minus 1 versus mole fraction of enantiomer. Okay. I think everybody knows this, but I will give some information. When polarized light enters in the liquid crystal sample, 2 rays are observed. One is extraordinary, the second one is ordinary. And extraordinary ray is parallel to the incoming polarized light, and perpendicular is the parallel to the incoming polarized light. So the difference between 2 rays is called double refraction of birefringence, and it is very important for the nematic phases. And another parameter is the magnetic successivity anisotropy. And as you know, liquid crystals are diamagnetic, and for diamagnetic materials, this is proportional to the magnetic field strength. And when magnetic field is parallel to the optical axis of the phase, it is represented by sheet parallel, and when magnetic field is perpendicular to the optical axis of the phase, it is represented by sheet perpendicular. So the difference between two magnetic susceptibility is given by anisotropy of diamagnetic susceptibility. And there is relation between the diamagnetic susceptibility, anisotropy, and double refraction. And if diamagnetic susceptibility is smaller than 0, the other is greater than 0 or vice versa. Okay. I give some information about optical and magnetic properties because they are needed to explain this picture. And this is the oriented nematic phases inside the when it exists in the microslide, and these are the aligned region, and these are not aligned. This is side of the microslide. And if this pseudo-isotropic or homotropic texture analyzed by conoscopy under polarized light microscope, the cross-dark brush is observed, and if we put the retardation plate incoming headlight, so you can observe this interference colors. If the colors in the direction of retardation plate is like this, This is called delta is positive. This means that phase director is perpendicular to the applied magnetic field direction. And the other one is this picture, and if you observe this color in the direction of retardation plate, this is called delta is smaller than 0. Okay, this is last information. Okay, according to our study, this mechanism is very important for us. There are two models in order to explain chiral induction in the chiral nematic phases. One is a chiral dispersion interaction model. According to this model, the chiral molecules between two adjacent micelles interact to form helix structure. And in the second model, when you add a chiral molecule into the nematic phase, one surface is turned like this, the other one is like this. So distorted micelles can be obtained. Then the chirality is transferred to the Hull phase. So the purpose of this study is to make a contribution for understanding of the chiral reduction mechanism in addition to these models. Because this chiral reduction mechanism is also discussing. Okay, for this study, we chose two racemic amplify. We have potassium aldopenoid alanine and its alanine, and we have potassium aldopenoid DL and L78. We chose this amplify because the chiral nematic phases by using alanine has pure chiral interactions. In other phases, induced chiral nematic phases, you add chiral molecule to the nematic phase. So these are more advantageous than the other ones.
I didn't understand because you could use, for example, lithium.
Sorry?
You choose to use left.
Okay, why don't we
okay, there is no reason to choose one.
Okay, generally it is not important because if you choose the DL
okay,
same, but I think alanine is more cheap.
Okay.
More cheap. Okay, in this study we used 5 different techniques. Polarized light microscope is was used to describe textures of the samples, and in addition we used it make colonoscopy in order to understand the orientation of the phase director. The second part is mass density method. This is very interesting method. As I talk about later, we can determine the micelle difference between DL and L anomers, but microscopically, not microscopic level. And small angle X-ray spectering was used to evaluate the micelle dimensions and the distance between the micelles. And laser light diffraction is used to measure helical pitch. And viscosity method is used to evaluate intermicelle interaction parameter, which is called Huygens constant. And we used small angle X-ray spectrum Bruker nanostar. It is similar in this group. And I think everybody knows this animation. No, this is the cuvette, maybe cuvette, I say cuvette? No. But, okay, we put the sample here, the crystal sample here. This is the light source. This is the two-dimensional detector. And this is the part between the detector and liquid crystal sample. as I said before, the detector is two-dimensional detector, so we can evaluate micelle diameter and micelle thickness at the same time. It's a very, very sensitive machine. Okay, according to Sharp-Link groups, there is two possibilities. Phase director can be perpendicular to the incoming X-ray and parallel to the incoming X-ray. And in this configuration, you can obtain ellipsoid-like Sachs pattern. One is arising from the micelle diameter, and other one is micelle thickness. But in this configuration, you can observe circular-like Sachs pattern. This is, as I know, this is known as obtained for isotropic systems. Okay, this is the laser light setup to measure pitch length. This is the laser source, and this is the obtained first order diffraction pattern. If you know the distance between this sample and diffraction, we can easily determine the pitch. And here is the equation. Okay, we used polypole viscosity method. It is a closed system, so we cannot lose any water, and it is very sensitive. And from this measurement, we can obtain the viscosity of this solution and viscosity of water. We can calculate specific viscosity, and if we can plot this value versus this value, we can obtain intermicelle interaction parameter pH. It is called the Huygens constant. This is the intrinsic viscosity. It can be obtained from intercept of this curve. Okay, now this is the results of the experiment, and this is the characteristic shearing texture of the nematic phases. When it is equilibrated in enough time, you can observe this type of pattern. Here, inside of the microslide, and the phase director is the perpendicular to the applied magnetic field. I mean, micelles oriented large glass surface. When we applied the conoscopy to these phases, and the characteristic colors for ND minus are observed. And this is the texture of the kinematic phases, and the helix axis is perpendicular to the glass sides. Okay, this is the pitch measurements obtained from the laser diffraction method. As you can see, for all enantiomer concentration, alanine system has smaller pitch. This means that in the alanine system, micelles are more distorted, as I said before. And this can be explained by the situation in the chiral. This is the part of the chiral micelle. In the alanine system, there is no hydrogen bond because hydrophilic group has a CH3 group. But in the same group, there is additional OH group, and it makes hydrogen bond surface of the micelle. So, in the cell system, the micelle surface cannot turn efficiently like in alanine system. Okay, as I said before, the mass density measurement is very interesting. We can publish the results in the physical chemistry, chemical physics, and by keeping all phase components constant, we replaced the N enantiomer but by enantiomer step by step, the density of the phase increased. It's very interesting, and we can explain these results by molecular arrangement in the micelle, a possible arrangement in the micelle. In the DL system, there is repulsion. There should be repulsion between these 5 carbon groups, between the carbon groups. But in the enantiomer system, there should be hydrogen bonds. So micelle in L system should be more compact than the other systems. We replace this experiment by using semi systems. We observe the same results.
No, in this one, you could see, instead of this arrangement, maybe you could have a DD.
Yes, you are right.
A DD and
yes, at the beginning of the
microphase separation.
Yes, you are right. But as I said, this macroscopic level. Later I will talk about such results. They support this possible arrangement. Okay. And in the semi systems, we have same results. And there is now there is 2 repulsion groups in the system, and there is hydrogen bond in the L systems, and this the micelles in this phase should be more compact than the other ones. Okay, now these are the slide in the scattering results, and these are the textures of the nematic phases in the mark capillary. I think it is called mark capillary in the Sachs tubes. In the middle is the liotropic texture. It means the micelles homotopically aligned to the glass surface. Okay.
In this case, you had magnetic field applied?
No, for ND phases we don't apply.
In this capillary, in this image you showed?
No. There is no magnetic field for ND minus phase. We don't use. It isn't used, sorry. Homotopic spontaneously aligned.
Yes, but in the walls, the micelle should be aligned in contact with the walls.
Yes, you are right.
And the director is homotropic aligned. And then in the center, you have a line of discrimination line. No? Because you have this homotropic alignment in the walls. So there is a defect here, because they cannot be gradient oriented.
Okay, you're right. Okay. In this configuration, the micelles, this is the micelle schematic representation of the micelle orientation. This is applied, this is microscopic diagram because we don't apply magnetic field. And in this configuration, then we can apply 2 graph values. First one is parallel, second one is the perpendicular, according to this Sachs pattern. And this is the Bragg equation. I think everybody knows the equation. And we fit the results to Lorentzian function. The values are very good results. And this is the chiral nematic phases before applied magnetic field. The helix axis perpendicular to the short capillary axis. And if we apply the Sachs experiment to these phases, we can obtain circular like isotopic phases, Sachs pattern, and we made the result of the isotopic distribution of the helix axis in this result in the Sachs tube. But these are my suggestion. I think different experiment should be repeated to understand these phases. And we explain these results by isotopic distribution of helix axis. And if you integrate these parts, these two directions, and if we apply racemic function to it, and the same d values are observed. I mean, it cannot be possible to determine micelle diameter and thickness. Then we applied magnetic field to kinematic phases because we changed the direction of the helix axis, and we obtained this texture. This is the same as this phase. I think it can be seen. Can be seen? Okay. And now the cholesteric stripes are perpendicular to the short capillary axis, capillary sides, and helix axis is parallel to the long capillary axis. And we applied the Sachs pattern, Sachs experiment to the phases. We obtained ellipsoid-like diffraction. And as you can be seen, micelles turns around the helix axis, and the diffraction arises from the thickness of the micelle and diameter of the micelles. And we fitted the results to again Lorentzian function. Now we have two different Bragg values, and these are the results obtained by the Sachs measurements. If we replace by L-racemic by dl in the sample, like in the mass density measurements, and we observe that as the L-racemic increased in the mixture, the perpendicular that smaller value, but the parallel almost constant. And we repeated the experiment by increasing the concentration. I mean, we tried to evaluate or determine the concentration dependence of the Bragg values. As you can see from this table, if we increase the concentration of amphiphilic molecules in nematic and kinematic phases, the Bragg values that's smaller. Yes, at the same time, the parallel values are smaller as the concentration does increase. And these are, I think, these are the same the results for alanine systems. We have similar values for serine systems. Now, and the Bragg values include the water molecules around the naked micelle. So we should subtract the effect of water around surrounding the micelle. This is the model which can be found in the literature, not our model. And periodic volume for this like micelles can be obtained by this equation. If we subtract the volume fraction of micelle or water, we can obtain the volume of naked micelle, exact volume of the micelle, and this value can be obtained from this equation, and this value can be obtained from this equation. All these equations are found in the literature. Then This equation is the corresponding to the Meiser volume equation. But here there is a problem about there is two parameters which are unknown, the diameter and thickness. So we should have make an assumption. The Meiser thickness is approximately equal to the thickness of the bilayer, and it can be obtained by this equation. This is known as Tam-Force equation for amphibolic molecules. Then, according to our study, we should determine the distance between two naked micelles. If we suppose two micelles is neighboring, and we can calculate this. This distance is very important because the distance corresponds to the distance between the chiral micelles along the helix axis. Then we oriented these parameters from the source results by keeping the total amplified concentration constant, and we replaced L enantiomers with the L racemic mixture, and we observed that the micelle volume decreased as the enantiomer are increased in the mixture. And it can be seen that if we increase the enantiomer, the distance between two micelles also decreased. These are the results for concentration dependence of the micelle volume and the distance between the micelles. If we increased the DL concentration in sample, it's always decreased, and for L enantiomer is also decreased. In all cases, L enantiomers has smaller micelle volume than GL counterparts. This means that always L enantiomers and the micelles obtained from L enantiomers are more compact than the L racemic mixtures. Similar results were obtained for serine systems. And the nematic phases has a smaller micellar volume and smaller micellar distance. And this is the similar to the aligning systems. Okay, now we need as you know, micelles turn around to complete 2-pi rotation along the helix axis. So we should know the screw or twist angle, going from one micelle to another, and we draw this type of configuration. And now we know periodic volume in fluidic water. It corresponds to the perpendicular, and we know the total distance between the distance along the helix axis, so we can calculate the number of micelles along the helix axis. Then if we know number of micelles along the helix axis, and we know that 2 pi is correspond to the 260 degree, we can obtain twist angle. Okay, this is the results for L-aligning system. If we increase the concentration of the L-aligning system and the D value decreased, micelles also decreased, and the twist angle increased, because as I showed before, as we increase the concentration of the enantiomer, the helical pitch got smaller. This is normal. This is the expected result. And this is the results obtained for enantiomer system. the results are approximately the same. I mean, as the concentration of racemic increased, the perpendicular decreased, and the twist angle is increased. Okay, this is the last experimental technique, viscosity measurement. If we applied this equation and we draw the curve, this versus this part, and the slope gives 2 pH values. As you can see, this value for elements units are always smaller than the real racemic mixtures. Okay, and this is our model to make a contribution to the chiral induction mechanism. As I said before, there are two common interaction model chiral induction mechanisms published by Ratley groups, Ratley and Solfer. And this is very interesting, another theoretical study in the literature, and which is published by Berard groups. And they calculated potential energy versus the distance between the solvent and micelle. And they suggested that the maximum twist induced by short-range chiral interactions, and it has maximum value when the two faces of micelle and solvents nearest to each other. I mean, the distance between the molecules or micelles is very important, as I explained in my studies. So these are I summarized some important results for you here in this table. And as the concentration of the amphibolic molecules increased in alanine and serine systems, and the distance between the chiral micelles in alanine and serine systems gets smaller. I mean, as the concentration increased, the micelles get close to each other. This is the same as for the serine systems. And another important parameter is Weissner volume. As the concentration of the amphibolic molecules increased in the liquid crystal sample, the Weissner volume gets smaller. And this is the another important parameters. H liquid twisted power of alanine system is smaller than the serine system smaller than the alanine system, and alanine has higher twist angle, and the intermicelle interaction parameters are for alanine and serine systems are greater than the racemic mixtures. This is very important because this means that the chiral interactions are more stronger than the achiral interactions. It's very important. According to the results and the Berard's results, we can conclude that in order to transform chirality to the full phases, there must be a crucial distance and a critical micelle size. I think this may be the first evidence of the Berard's suggestion, because I don't see anything about these results in the literature. And as I said, I showed two different model chiral induction mechanisms. One is chiral spherical model, another one chiral pairwise interaction model. If we compare our results, Berard results, and these models, the chiral induction does not take place completely as was suggested by pairwise interaction and spherical interaction models. And but to anisotropic high interactions via distorted micelles, for which a chiral distance between the micelles and a critical micelle size are required. Okay, to go to the last one.
For questions, please.
You don't have? I didn't.
I made my questions.
This is the half part of my PhD because we made temperature dependence of these results, and it was supported these results also. Maybe later I can show these results in another seminar. Maybe.
Yeah, sure.
I was upset when you started. This is where you working when you did this.
Sex measurements.
Yes, all these.
Some part in Turkey, some part in Stuttgart. Professor Wilson's groups.
And this Berardi is Italian. Italian.
I don't know.
No.
Maybe I think maybe because the name is similar to Italian name.
Oh, it's very interesting. I made question because I'm interested.
In my master thesis, we made experiments by similar compounds, esters. We used esters, and we applied distance measurements to that to those systems, and we observed the same results. But as I said before, the results are macroscopic level. So we should apply the experiments for microscopic level. So we applied the Sachs measurements. Sachs measurements are gave very, very wonderful results.
And you are going to stay here during 1 year.
Yes.
And what is the project?
About biaxial nematic basis. We will produce new biaxial nematic basis.
Mixing of surfactants.
Yes.
But not chiral.
We started with potassium chloride, but this is the educational study for me because I don't know what are biaxial nematics. Then I think we will use potassium chloride, and I'm trying to different phases.
We can do this experience. I have suggested to Christian to prepare biaxial phase.
Yeah.
To prepare a sample with different phase, nematic, uniaxial, biaxial phase, and to do such experiments because we can model this. And if you could, yes, and it would be very interesting to answer a question that maybe there is some controversy about this. If the micelles are biaxial objects or if it's a mixture of discs and plates, discs and cylinders. But as we can model, maybe we can answer this question. For example, if you prepare the sample and you choose the temperature where it is in the uniaxial phase, for example, and I think it's important to work with the oriented samples, and this will have to develop some method for oriented samples. But in the discrete phase, in the cylindrical phase, it's not different. In the biaxial phase, it's complicated. You can do such experiments, and then if you model the spectrum, maybe you can see if the object is a cylinder or is a disc or is a biaxial object. Maybe it's not possible. It's really an adventure because there are not many peaks to have all of this information. Maybe it's not possible. If it could be then it would be very interesting.
Which are the diameters of the capillaries that you have made?
0.7.
1.7. 0.7. Okay, so they are very small. And which was the size of the X-ray beam?
As I know, 1 millimeter. It's X-ray. 1 millimeter.
So the beam was larger than the capillary itself.
But
so
there is something during the biaxial phase. I think that, for example, if you make a cell as you have with these microplates, to introduce the sample between the microplates with a very sequence, because then we know that they will orient by surface effects, it will be oriented. If you, if there's some time to get equilibrium, but if you see a liotropic texture, you are sure that it's oriented. And then you can make the experiment.
So, do you have more questions?
I have a technical question.
Sure.
Could you show again, please, the sex equipment, the nanostar? So, no, yes. It's really similar to which you have here, from the sample chamber to the detector. But it's really short at left. I mean, here there is the light source, the X-ray source, and two pinholes more or less 1 meter apart one to the other.
I saw yesterday.
Yes, this was the first version of the nanostar. The problem of this machine is that with this you have a very large background. So this machine is good to measure things that scatters a lot. But if you are studying, let's say, sample that has a very weak scattering, you have a very large background, so your lab will be much more difficult to measure it. This machine, Professor Jens Christian from Denmark, he bought this machine like this, and then he made some calculations and optimized this front end to have to have that beamline the design that later was incorporated by Bruker in the new machines. So that's the answer. Okay. Yeah.
I think you're mentioning the new version of
Yeah.
the version.
Very good. So if you don't have more questions, let's thanks again. Thank you.